Hello, welcome to AP Calculus Review Part 1. We'll first be covering limits. So let's recall what a limit is. Let's say we have this point right here. You find the limit at this point. You can approach it from the left, you can approach it from the right. It's not considering the actual value, it's just what the y value that you're sneaking up on. So this could be considered, let's call it k. The limit as x approaches, let's say a, of the function f of x is equal to k. You can also write this with left-sided and right-sided notations. The minus means you're coming from the left side. You're just considering creeping up on this y value from the left. The plus means you're creeping up on it from the right. You can also have limits in tables. Let's see, we have 2.9 and 4.9, 4.99. And we have this table. We want to find the limit as x approaches, let's say 3. You can see as x approaches 3, it's going to 2.9 to 2.99 to 2.99. It keeps getting closer to 3. This y value also keeps closer. 4.9, 4.99, 4.999. It gets closer to 5. And you can also so you can see limits in graphs and tables. Limit properties. If you have the limit of two functions added together, that's the same as the limit of the first one plus the limit of the second one. Same thing for subtraction. If you have one function minus another, the same as the limit of the first minus the limit of the second. Same thing for a lot of these. If you have the limit of two functions multiplied, then it's just the limit of the first one times the limit of the second one. Same thing, you have a function over another. It's the limit of the first over the limit of the second. If you have the limit with an exponent, or with an exponent, then you can move the exponent to the outside. If you have a constant, you can move outside the limit. And last, if you have the limit of a composite function, f of g of x, then you can just move the limit inside of the function, say f of the limit of g of x. Your basic limit properties. Squeeze theorem, let's say you have a function, it's between this top one and this bottom one. And let's say we have at x equals 0 here. You're going to find the limit of f of x, which is this blue shaded area. And since this is squeezed between these two functions, let's say this is 2. And because you have the limit of the top one is 2, the limit of the bottom one is 2, and they squeeze f of x together. And since f of x is between the top and the bottom, that means the limit of f of x is 2. That's the squeeze theorem. Infinite limits. These apply to vertical and horizontal asymptotes. Let's cover vertical asymptotes first. Let's see the function that looks like this. And you want to find the limit as x approaches 0. You can look from the left side, it goes up to positive infinity. Right from the right side, it goes down to negative infinity. And since the two limits aren't equal, then the two-side limit doesn't exist. Let's cover horizontal asymptotes as well. This is when you have limits where x approaches infinity or negative infinity. And we have to find what y value the function approaches as x keeps going on. You can find, let's have 3 examples of these. Let's say limit as x approaches infinity. If the degree of x is greater on the top than it is on the bottom, say you have 2 on the top and 1 on the bottom, then the limit's going to be infinity, because you have infinity squared on the top and just infinity on the bottom. This is infinitely more than this, which means this limit will approach infinity. If you have a greater degree on the bottom, then the limit will approach 0. And if you have the same degree, say x plus 2 or 3x plus 3, then you can consider these void. Those don't matter. We're just considering our x values, our highest degree. We have x over 3x. Those would cancel out, and we'd be left with 1/3. It's the same for anything. If this is 2 over 5, these would still cancel out. This would become 2 over 5, and so on. Discontinuities. There are 3 main types of discontinuities. You have removable discontinuities. It's like a point is just removed from the function. Removable. You have jump discontinuities, where the function jumps. And you have infinite discontinuities. These are basically vertical asymptotes. There are 3 conditions for a function to be continuous. First, that the function is defined if it has like an actual value. The limit exists, it's also defined. And the limit is equal to the actual value. So let's say we have this right here. Let's say this is the point. This is defined, f of c. The limit is also defined. You can see the limit approaches its true value. This is a continuous function right here. Intermediate value theorem. This basically states that if you have a continuous function like this, you have, let's call this a, and this point b. So this y value would be f of a. This y value would be f of b. And if you have a y value, let's call it k, in between here, the intermediate value theorem is like, if you want, so if you want this k value between f of b and f of a, and it's continuous, it's guaranteed that you'll have an x value associated with it, which in this case, we actually have 3 of them. This is 1, this is 1, this is 1. If it's not continuous, let's say we want k to be here, f of a, f of b, then the intermediate value theorem doesn't work. So basically, if it's continuous, that means there's an x value for the y value. Indeterminate forms. You may encounter indeterminate forms like 0 over 0 when you're evaluating limits. And when you encounter something like this, you can use L'Hopital's rule, where if you have the limit of something, and it's like 0 over 0, then you can take the derivative of both sides, the top and the bottom, and this will still give you the true value for the limit. Alright, next up, we're going to cover basic derivatives and the rules regarding them. So remember, derivatives are like the slope of a function. You want to find the derivative at this point. this line is called a tangent line. This represents the slope at this point, the derivative at this point. So the derivative as a limit, it can be written two ways. First, like a general derivative, it would be the limit as h approaches 0 of f of x plus h minus f of x all over h. This will give you like the general derivative of a function. And you may also find one for the derivative at a specific value, which is c. That'd be f of x minus f of c over x minus c specific. It's important to recognize these formulas because we encountered these on the AP test. Derivative notation, you can write derivatives many ways. F prime is one of the most common. You also have dy over dx. And some, I haven't seen this, but you may write like d of like a function. There's always, you may see derivatives written down. You'll only find these on the AP test most likely. You may also find higher order derivatives, like f double prime, f triple prime. So f double prime is just the derivative of f prime. F triple prime is the derivative of f double prime, and so on. Same thing for the dy over dx. You get d squared y over dx squared, or d cubed y over dx cubed. This is like taking the derivative of something over and over again. Average rate of change. The formula for average rate of change. Let's have a graph here, just for clarity. This is A. This is B. This is your f of A and your f of B. The average rate of change is going to find the slope of this line between them. We call this the secant line. Your average rate of change. The formula for that is f of B minus f of A over B minus A. Undefined derivatives, or where derivatives do not exist. If the function has like a cusp or a corner, then the derivative doesn't exist at this point. If they have the vertical tangent, like this, then the derivative doesn't exist. And if they're discontinuous anyway, then the derivative doesn't exist. These are all conditions for like differentiability. It has to be continuous. Can't be a vertical tangent because then you have like an infinite value for a derivative. And then if you have like a corner or like a sharp point, basically, then you can't derive it at this point. Graphing derivatives, you should know how to graph derivatives based on their original function. So usually when you're graphing derivatives, you want to find where the graph like changes from increasing to decreasing. So here it's decreasing, increasing, and increasing right there. These points where it changes from increasing to decreasing, you're going to mark those on your x-axis because that's when your derivative is 0. If you have an increasing, then it's going to be above the x-axis. If it's decreasing, it's going to be below the x-axis. So the derivative for this function right here would look something like this. Differentiation rules. Power rule. If you have the derivative of x to the n, that's equal to n x to the n minus 1. So you take this n, multiply it, and decrease it by 1. Take the exponent, multiply it, decrease it by 1. The derivative of any constant, that's like the derivative of 100, the derivative of 1,000, derivative of 1. The derivative of a constant is always 0. If you have a coefficient, let's call it c, then you can just move it out of the differentiation to move it out. This may help if you want to, if you have like more complicated derivatives and you want to just take this coefficient out to make this a lot easier. Sum and difference. If you have two functions added together. You try and take the derivative of them. It's just the derivative of the first plus the derivative of the second. Same thing for subtraction. If you have one function minus another, then it's the derivative of the first minus the derivative of the second. Product rule and quotient rule. However, unlike limits, where limits you just do like, okay, the limit of these two functions multiplied by each other is just the limit of the first one times the limit of the second one. But you can't do that with derivatives. There's a special formula for that. The derivative of two functions multiplied by each other is f prime g plus g prime f. Have to memorize this. Same thing for quotients. There's another rule for one function divided by another. So it's called the top one f and the bottom one g. So if f prime g minus g prime f over g squared. I have to memorize this one too. And finally, tangent lines. The formula for the tangent line is going to look like y minus y1 equals m x minus x1. This is point slope form. It's the easiest to write tangent lines in because sometimes you'll be evaluating the derivative at a point. Let's say you want to evaluate the derivative at x1. Right, first you'd find the actual value, y1, and then m represents the derivative or slope. Let's plug these in. Let's just put some values for example. This would mean at the point 1, 3, the slope is 2. Alright, so if you have a negative x value, you're going to want plus here. And if you want a negative y value, you're going to have plus here. Alright, that's all for part 1. See you in part 2.